In train tracking 2, Bessie is going to be looking outside to see an express train. For every sliding window of k, she's going to get a value that represents the minimum label on any carriage within that range. We want to give the number of ways we can assign the different labels of the carriages so that all of the carriage labels are not exceeding 10 to the power of 9. Let's solve an easier version of the question first. If we assume we have a range where in the input all of the values are the same, like for example 3, then what we can do is we can create a DP to help us solve the question. We're going to create a DP where the state is DPI, meaning that we are currently on index I, where we're going from 0 to I, and the ith value is going to be equal to v. So the ith value has to be assigned v, or v is the input value. So if we have our state, the next thing we need to work on is our transition. If we assume we already know the value of dpi minus 1, then we can assume that for this value, where we're using dpi minus 1, the value here is going to be assigned v. Since that's how we defined it in our state, we defined that the last value is going to be v. Since we have a v here and we don't know if there's going to be a v here, we're also going to assume we have v at I minus k minus 1, since I minus 1 only covers up to here. So if we know how many combinations there are for this, in order to calculate dpi from going from dpi minus 1 to dpi, we can assume, just like in our state, we put a v here. And we can also assume that since in dpi minus 1, we know there is only one v here, in order to move one state over, we're going to need to basically allow this to be any value from v all the way up to the maximum. So we can define a value x as the maximum value minus v, where this is the number of numbers that we can assign so that the value is going to be greater than v. So this is all of the numbers we can assign. And then, so if we were to go from 0 to v, with the only difference we need to make right now is to change this value from just 1v to any value from v or greater. So that's going to allow us to make the transition state. dpi is equal to dpi minus 1 times x plus 1. Since this is going to be the number of different values we can now assign to I minus 1. But the thing we need to note is, since our sliding window has size k, this is actually going to do overcounting. And the situation where it would overcount is, since we know that this v originally covered this area, so all of these numbers could be greater than v, when we move this v here, so if this number is not necessarily v, then there's going to be a state or a sliding window where it's not actually covered, meaning we've added a state which is actually not going to work, since this is only going to cover up to this is only going to cover up to this, where this value or this sliding window here is not going to have any value of v if I minus 1 is not the value of v. So by moving our v over 1, we're basically moving our entire sliding window of things covered by this v over by 1, meaning that there's going to be a scenario where this is not in fact covered by v. And so what we can do to account for this specific scenario is we can basically subtract the value where all of the values here are greater than v, and then multiply that by the number of combinations here. So all of this is going to be the same, but from here to I, so this size here, if all of these values are greater than v, then this is not a valid case. So we counted it here and it was fine because we set this value to v, so this was definitely covered. But since we moved the v over 1, there is the scenario where all of these values are now greater than v is going to be invalid. So we're going to need to subtract that value. And so that's going to be this part here, dpi minus k minus 1, and then times x to the power of k. Since all of the values in this k range have x options, so it's just going to be x times x times x, and then so x to the power of k. We're going to break down our input into different sections. So we're going to have, for every group where it has the same value, these are all going to be individual windows. For some sections, for example, this sliding window here, it's going to be covered by 2 windows. So this one is covered both by the 3 and by the 2. And so if we were to just directly run our DPs with, say, this window, this window, this window, we might end up with the wrong answer, since we're going to tell our program that this section here only has the restriction of being greater than or equal to 2, when in actuality, because k is equal to 3, it needs to be greater than or equal to 3. So what we're going to do instead is we're going to actually check the beginning and the end and go over for every range a bit. Since we know that whichever number is greater is going to have more restrictions, so like for example in this range, since 3 is greater, we know that this range here has to be greater than or equal to 3. So whenever we come on a new window, we're going to first assign it the range of the actual range from the input, and then plus k minus 1. And then we're going to check if the value in the next window is less than this value, then the 3dp is going to take this range. If this value was something like 4 instead, then the 4 has more restriction on this window, so this bit here actually has to be covered by greater than or equal to 4. So then we'll just subtract this value, and then for the 3dp, we're only going to run this. And then we're actually going to do the same thing for the front. So if it's not the first window, we also have to check to see if the previous window actually intruded or went over. So in this case, since 4 is greater than 3, the area here, so from 4 to k, so this k window here, is actually going to take up these values. And since 4 is greater than 3, we know that the values here are actually going to be run with 4's dp. So we've already used the dp with these values, or actually these values down here. So I'll show this more in the code, but basically when we run a dp range, we're going to check the beginning and the end. So if the end has stuff smaller, then we're going to add it. And if the beginning has things greater, then we're going to subtract it. Let's go look at the code for this question. After we read in the input, we're going to loop through all of the values. So we're going to use a 2 pointers mechanism with I and j, where j is just going to continually move forward, and it's going to represent the different ranges or different windows where all of the characters are the same. So I is going to be the start and j is going to be the end. We're going to keep incrementing j, and then what we're going to do is we're going to look at the length of our current window, and then we're going to change this length depending on whether it's greater or smaller than its other values. And what that means is we're first going to add the extra k minus 1 for the second half. So since it's going to go over k minus 1, then we're just going to add that to our length. And then we're going to check this against our previous window. So if this is not the first window, so we'll do special handling for that, we're going to check to see if it's already calculated the first k values in the previous window. And if it is, then we don't want to overcalculate our answer, so we're just going to subtract that k from our length. We're also going to check against the next window. So as long as it's not the last window, we're going to check to see if the window after us is going to calculate the last k values in our current window. So if they're going to intrude on our window. And then if they do, we're just going to subtract that for the same reason in order not to overcalculate. And then if the length of this current window is still greater than 0, then we're going to use our dp. And the 2 parameter values are going to be the value of everything in this current window, so vi, and then the length of the window. For useDP, we're going to create a function. So we're going to first have our 2 parameters, and then we're going to create our dp length plus 2. And this is just because we need to add that extra element to the end. I'm going to initialize the values of dp1 as 1, since at the position 1, there's going to be one way, and then dp0 doesn't really matter. And then we're going to have our value x as m minus val, meaning x is all of the different possibilities that we can put as long as the value at I is greater than val. So that's the number of ways. Then we're going to start our main loop. we're going to have I starting from 2 all the way to length plus 1, since we're going to be going over 1. And then we're just going to do the dp state. So dpi is going to be equal to dpi minus 1 times x plus 1, and then we're going to mod, and then we're going to check to see if I minus k minus 1 is greater than or equal to 0, and if it is, that just means we need to subtract the previous value or the overcounting. So we're going to make dpi the value of dpi, so this value here, minus, and then we're going to do dpi minus k minus 1 times x to the power of k. And then since we already did a mod on this value, there is a possibility that this mod is going to be less than this mod. So we're going to add mod and then mod it again just to make sure we got an accurate value. In order to do fast power, we can just copy over a function, and this is the very standard fast power mod function. At the very end, we're going to return the dp length plus 1 mod. And then at the very end here, we're going to multiply our answer by this Windows value, and then we can just output our answer for this program. So that's the end of our program.